in half.
Huh?
Oh, man.
Oh wait, that doesn't seem that bad. It's just like that angle divided by 2, or maybe not.
Yeah, there's more to it than that.
Oh, there
So-
always is.
Oh.
I'm now dividing this by 2, and the question is, what's the acceleration? We're still keeping it frictionless, so 9.375. There's potentially rounding issues in there. What changes in our force diagram?
The acceleration. Oh, and the angle for, on the mass 2 box.
Okay, but how does that, so we have a value for theta of 9.375 now.
Yeah.
But other than we have a value for theta, anything in our force diagram change?
No.
Yeah, somebody mentioned acceleration. Acceleration is not part of the force diagram, that's the next step. All right. These change. I would say, just for the sake of this, just to see what happens, let's keep our coordinate system the same. Although you might logically think, oh, we should probably flip I, but let's not. So that changes. Well, some of that.
I didn't see what changed.
I erased the right-hand side.
Oh, okay.
Hold on.
So that is what's changing?
Yes.
Yeah, because we're.
Well, two of them will stay the same, but 2 of them will change.
Because we're 9 and something degrees short now, right?
Yep.
So, but how do we decide where it's supposed to go? Does it just go with that, like, do we just add that to the 40 degrees and call it a day?
Well, the only thing I changed was that angle right there.
So that's accelerating to the left and down?
Oh.
So, if we keep the same coordinate, there's nothing wrong with keeping the same coordinate system. If we get a negative acceleration, that means, oh, it went the other way. If we get a positive acceleration, we got it right.
Yeah.
Or we have it in the direction that.
Wait, couldn't we
Yeah, we
replace
thought wrong.
theta then? Because we know the angle.
Yeah, okay. So,
9.3.
9.3.
Oh.
Okay, smart guy. Definitely seems like the easier one.
I was gonna wait to do that, but you know, what the heck, you can spoil the surprise now.
Oh.
Will?
So we keep the 40 and then the extra goes to the top angle.
Yeah, well, the angle at the top is gonna change now. Yeah, so basically, assuming that's a 40-degree angle. If this angle gets cut in half, then basically this becomes a lot longer.
Oh.
Do we set all the equations equal to FMA?
That's what we need to consider. All right, so is this gonna be now, is this 0 still?
Oh,
Or is
wait.
this changing?
Well, it's still in equilibrium, right?
Well, are we still?
No, not in equilibrium anymore.
Because now.
Well,
It was in equilibrium with that other angle, but we've changed that angle, so it can't be in
What we need to
equilibrium.
consider is, I mean, in my mind, it would be like what I asked before, is M1 going down and to the left and pulling M2 up and to the left? Or, yeah, or is M2 going down and to the right and pulling M1 up and to the right?
Are we there
We'll
yet?
figure
find
it out.
Yeah.
All right, so what is this equal to?
Mass of 5 times acceleration?
In this equation?
Mass of 5 times. Oh, wait.
Is that what you're saying?
Is it just 0?
Yes. This is still 0.
Okay.
Because the acceleration is along the ramp, it's not perpendicular to the ramp, so that's, again, we pick our coordinate system, hopefully with the idea that one of these will be equal to 0. And likewise, that'll also be 0.
Oh, I was about to say that one.
So this one,
M10A.
and those A's are the same because it's an ideal rope, it's not gonna stretch, it's not like one of them's gonna start moving before the other one starts moving, they move together.
And then we could, and then we could find f of t, and then, plug in all our stuff and yeah, and then divide by M5 and M10 and we'd have our accelerations, no?
I believe you, but I don't know.
Could we multiply this top?
I can't even
equation
think
by
it big
2,
today.
Do we
And then-
substitute what we,
Take out the A.
What are we looking for?
All right, if we multiply the top equation by 2, which I heard one suggestion. We'd have M, this would be 10A, this would be 10A. What ultimately we're trying to find A.
Yeah.
So if we did that, we're shooting for trying to find tension so that we could find A. That is legitimate, but not necessarily the quickest.
Oh, okay. What's the quickest? This is what we gotta know.
The way that your mind is working at
Does
that
G
moment, so-
still apply?
Well, I would've done that multiplying by 2.
What's that?
Does G still, because we made, so f of t was equal to m5g
Yeah.
sine of 40.
G now matters, so let's put it on Earth.
Okay.
No, let's put it on a strange world where G is equal to 10
Okay.
I like
meters
that.
per second squared.
I will come back
That's a
to
good
you when I
rule.
finish my calculation.
That would be nice.
It's the world of all metric freaks.
All we need is a few more.
So then those weights become 50. What-
So,
what-
oh, okay, we're now at the substitution phase. So we have tension minus M5G sine of 40 degrees is equal to M5A. Again, because there's no acceleration, because there's no friction, our normal force equations really have no bearing in this particular problem. Normal forces are perpendicular to the motion, and so, back up for a second. Because there's no friction and the normal forces are perpendicular to the motion, or perpendicular to the acceleration, those equations will not have any bearing on this problem. And then we have M10G sine of 9.375 degrees minus tension is equal to M10A.
Okay.
Yeah.
So is
You set both equations equal to force of tension, and then we
oh yeah.
set those equations equal to each other.
Yeah, we could.
Could we also, just out of curiosity, could we multiply the top one by 2 and then just because that makes that M3
Dan's
equal to
had a good
M5.
idea.
If we multiply the top one by 2,
He was 8 and under.
and then potentially we could then cancel these out.
Yeah.
We'd have 2 FT here and FT there. We could do that, solve for tension, and then, plug it back into one of these equations to find acceleration.
Okay, so you can do that.
Yeah.
I don't think that's the way we should go, but I was just curious if we could.
Alright, there's also the suggestion of just solving for tension,
Yeah.
so,
I've ran into it. Wasn't tension equal to m5g sine of 40? Like
in the
how-
last problem,
In the, oh, it doesn't.
it's not in equilibrium anymore.
Alright, okay, I was just kinda going crazy until I hit a roadblock.
So FT is equal to M5G sine of 40 degrees plus M5A. We can take that, plug that into the second equation. And there's a technique which I feel doesn't work, but. 375 degrees minus that. So 10A. Force diagram there. I'm assuming people are good with
Wait,
what this problem looks like.
What does that say in the parentheses there? Next to M10G sine?
This,
Yeah.
that,
Oh,
it
okay.
just substituted in for FD.
Oh.
So we now have M10G sine of 9.375 degrees minus M M5G sine of 40 degrees minus M5A is equal to M10A.
Oh, I see.
That's some number calculator exercise. Bring M5 over. And so we have something that's equal to 15A. And this is one of the reasons why I personally will do the subscript is equal to the mass, just so that I don't have to go back to, what was the mass again? And I'm carrying it along with me. But that's a personal preference. If someone would be kind enough to, actually, if you could tell me the individual values first and then the sum or difference.
I can tell you right now that M5G sine of 40 degrees is equal to 32.139 degrees. And then M10G and 10 sine of 9.375 is equal to 16.2895. Yeah.
And so the difference.
Oh. 16.2895 minus 32.139. Negative 15.488, no, like 8495. And then you divide by 15.
My rounding was a bit different, but I got negative 1.0587.
Oh, so that's not good.
All right,
0.06.
and because we were trying to find the acceleration, what are the units?
Meters per second squared.
Or,
Huh?
You say or?
Or. Oh.
some people use this for the units of acceleration in
What?
one of the.
Change
master
of
sets.
velocity over change of time?
Is it like
That would get you meters per second squared. doing it that
Meters,
way.
I don't freaking
meters, seconds,
Yeah,
to the
slash
negative
S,
2 or
slash
whatever. Is that the one you're looking for?
It's also Newton per kilogram, that's what I was looking for.
I forgot, how do you, what is it? How
F
do you
equals
say
MA,
that?
so A is equal to F over M.
Right.
So the units of acceleration should be also newtons per kilogram.
Newtons per kilogram.
Is that what you need on the test?
No, well, they're both correct.
Oh.
Meters per second squared is what I would expect, but if you wrote newtons per kilogram, that's fine.
Oh, that does make sense.
That doesn't
This
seem
much
that
for,
bad. Is that
for
like,
this much kilogram.
were those the two parts of the problem, or is there a second another one?
Oh, there's a third part.
Of course, it's there.
And that's the third part.
Friction, I always struggle with friction, I don't know why.
All right, so first off, let's interpret what we have here. We got negative 1.0587 meters per second squared is the acceleration. What does the negative sign mean?
That means it's
Moving
going
left.
The opposite.
It's going up.
opposite. Yeah.
So if there's friction, which way will friction be acting on this guy?
Up and to the left.
On the box, down and to the right.
Oh wait. Oh, it's like trying to oppose movement. Or no? Is it?
Mm-hmm.
Yeah.
It opposes the desired motion.
Yeah.
Now, if I gave, and it turns out if I gave friction for both of these, and it's not moving, well, I guess you have the acceleration right there. It gets a lot more complicated if you have friction in both spots. And so on the test, I said, just give one side friction. So let's give it to the left side. Any other questions before we throw friction into it? Make PJ happy.
When you're So when if this ramp is like the same material, so like the coefficient of friction should be the same for both of them, in theory? You don't have to solve.
If they're, I would assume that that would be the case.
Okay. So you don't have to like solve equations like
With
for
different
both.
mu values.
Yeah, I would,
Is there gonna be kinetic friction involved in any of this? 'Cause I
We'll
don't-
find out.
Oh, okay.
Is that part 4?
Is
Or part D?
I mean, there's two tacks I could take here. We know the thing's gonna be accelerating, or that's going this way, this is going that way.
Yeah. Well,
If I throw friction into it, I mean, one style of problem could be, it's now in dynamic equilibrium. What's the coefficient of kinetic friction? Or I could give you use of S, use of K, and ask what's the acceleration now.
I think I like the first one more, or no, the second one more, where you're like muse of S, muse of K, what's the acceleration? Or is that one,
Sure, let's do that.
is that one harder?
Cause there's an equation that relates them in the thing.
Yeah.
It's not exact, if I had a really big use of S, the thing, it's not gonna be moving at all. So we'll assume it starts at rest. There. So what's the acceleration now? So at this point, we can switch our I directions just so that we end up with a positive acceleration. Or we can keep I the way it is, and we can set it up so that A is gonna be a positive number by putting a negative sign on the right-hand side. Or we could set it up and, acceleration is negative is what we're gonna expect. But we've got some options here. I can do it the way that I would do it, or I could open it up to, if anyone has a suggestion of way
We
you
can
want
keep
to do it.
our I hats and J hats the same.
Okay.
That way it's like continuous with the rest
Right.
of what we've been doing.
And you want acceleration, you want our answer to be a positive number means it's still accelerating, or a negative number means it's still accelerating?
Negative. Right.
Negative still accelerating?
Yes.
Okay. Then, let's throw friction into it. So friction's acting, I think it's already been said, friction's acting this way. So we start out with the assumption that it is static, that we're not gonna overcome friction. So we have S of S going that way. I have only friction on the left-hand side.
Wait, so does that just change your equations of motion then?
It changes one equation of motion.
That would be the I hat 5, and that would be, we would add a positive F of S in
Yep.
there.
Wait, so there's only friction on one box?
Yeah.
Oh, so
I
there's
have,
not,
yeah, please explain.
It makes the problem more reasonable.
Okay, I like that.
I like that.
yeah. Yeah, cause it's just a problem. But realistically, like if it was really happening, there would be friction on that other box somehow.
Yeah, yes, if I were actually setting this up.
Yeah, okay.
The trouble is that we can go through and it's possible that we haven't exceeded static friction here, but we have exceeded static friction here.
Oh, so that could be.
And so now we're in the situation of, is it moving or not? Probably not, but that's why, just simplify it down to, we have friction on one, I can on one of them.
Are you gonna list that in the problem?
Yeah, I would say that problem. And, well, how much can we just adapt without actually having to change much? So we've added static friction there. So that changes this equation. We have an independent formula for static friction. Finger does not work over here. What's the formula for static friction?
Oh god, it's like muse of S times y or something.
Mm-hmm. No, you had it.
Okay, this is the maximum static friction.
Times what, the normal force, is that what it is?
Can we assume that it is?
You assume that it's not the maximum?
That it is the maximum?
Yeah, we're gonna assume the maximum. So, the way we have it set up, I know it's going to accelerate that way.
Yeah.
I haven't stuck an extra negative sign anywhere. So if I know it's gonna accelerate that way, and I'm expecting a negative acceleration.
Mm-hmm.
If I work this out and I get a positive acceleration, that means it's not moving. So we work under the assumption that we're at the maximum just to see if that makes sense.
Is that right there? Is that greater than or is that equals?
Here,
Yeah.
that's supposed to be an equal sign.
Ah.
So it wouldn't just be zero? If it was static, the acceleration wouldn't be zero?
Yeah, but we don't know it's static.
Oh,
So we have these dueling forces. I have the W5 sine 40 degrees act pulling this way.
Yeah.
I have W10 sine 9.375 degrees pulling it that way.
okay.
And now I have this other friction pulling it that way. So the question is this enough to overcome that and that? That's ultimately what we're working with here.
Okay, I see.
And so if those are greater, then we know it's not moving. It has not overcome the static.
And then
Okay.
you could find y using mg cosine theta.
And so, oh, that's Y5 there.
Oh yeah. And then
So yes, then we would use that.
so good.
We told you you had it when you were saying.
I'm just gonna erase this. There's a, that's the one.
I used y equals mg cosine theta more times last night than I've ever used it in my life.
Congratulations.
Yeah. I was very proud of myself.
All right, so we have tension, I'm gonna put the plus use of S times mg m5g cosine 40 degrees minus m5g sine 40 degrees equals m5